Ladies and gentlemen, welcome to Yokogawa's Analytical Web Seminar on Oxidation Reduction, Potential, Basic Principles, and Tools. We would like to thank you all for taking the time to attend, and we hope you find the seminar helpful and informative. Before we begin, we would like to go over some housekeeping issues. The audio part of this seminar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. The seminar will last approximately 1 hour, and towards the end of the presentation, where time permitting, we will have a question and answer session where our featured speaker will answer some of the questions received from the audience. If your question is not answered during the presentation, please be assured that we will answer them directly via email or telephone call. All questions should be submitted in either the question and answer window or the chat window located in the lower right-hand corner of your screen. And our featured speaker for today, again, is Sherilyn Marlowe. Sherilyn is the liquid product specialist for Yokogawa, and she has worked for Yokogawa for 3 years. And prior to working for Yokogawa, she worked as a quality assurance technician for Bondo 3M, and previous to that, she worked for a nutraceutical manufacturing company, Deerland Enzymes. As of now, we'd like to get the seminar started by handing it over to our featured speaker, Sherilyn Marlowe.
Thank you, Barbara. Just wanted to, again, thank everybody for joining us today. This is going to be the second time that we have run this webinar on oxidation reduction potential, just basic principles and tools, what it is, how we do it. We got a good turnout last time, and people asked if we would replay it for their coworkers so that they could come back and see it as well. So many of you might already use ORP measurements every day, but you may not fully understand what oxidation reduction potential means, and what we wanted to do is provide you with the basic understandings of how the ORP measurement is taken and what is required for the measurement in order to be successful. So to do that, we're going to talk about why you want to measure ORP, what is ORP, how is it, what do you use to measure it, and what is this thing called pH compensated ORP. Then we'll go over and we'll talk a little bit about some calibration and maintenance techniques that are commonly used, and then we'll dive into just basic level applications that we have. So ORP is a key measurement and control parameter for a wide variety of applications. Like I said before, we'll go into some more different applications in more detail later, but at a quick glance, you'll see ORP for corrosion control and bacterial growth in cooling towers, and you also will see it in wastewater treatments for cyanide and chromium reductions and the mining and electroplating industries. Go ahead. If you are already familiar with a pH measurement, you will find that ORP is similar in the fact that they are both electrochemical measurements that require a special high impedance input. Also, pH and ORP normally use the same standard silver chloride reference electrode design that we'll talk about later. However, ORP differs from pH because it uses different measuring electrode that responds to the oxidizing or reducing activities of the ions within the process solution instead of the hydrogen ion activity as seen in pH. So now let's take a moment to discuss what ORP, or oxidation reduction potential, actually is. Another name for this type of measurement is known as redox. This refers to the fact that within a process being measured, reduction and oxidation are occurring simultaneously. One cannot occur without the other. If one species undergoes oxidation or loses electrons, then another species must accept those electrons and is then said to be reduced, or it gains electrons. Within a redox reaction, there are always two types of species. You have an oxidizing agent and a reducing agent. In the reaction shown here between iron and copper sulfite, the two half reactions that occur at the same time are the reaction that takes place on the copper element and the second reaction that takes place on the iron element. In this reaction, the copper is considered to be the oxidizing agent because it has the capacity or potential to acquire or gain electrons and become reduced, while the iron element is considered to be the reducing agent because it donates electrons and is therefore becomes oxidized. Okay, so I know this sounds a little confusing because it's almost as if you see the terms are backwards. However, the oxidizing agents are reduced because they gain electrons by an atom, which leads to a decrease in the oxidation state of that element, while the reducing agents are oxidized because they lose electrons, leading to an increase in the oxidation state of that element. It's also important to remember that ORP is a quantitative measurement, therefore it responds to all ionic content within a solution, and it cannot distinguish between the individual process components. This is similar to what you see when you're measuring conductivity. So now let's take a look at an everyday example that you probably wouldn't have thought about. If you've ever wondered, and you may not have, what gives the sapphire crystals their deep blue color, surprisingly enough, this actually comes from a simple redox reaction that occurs naturally between the titanium and the iron impurities that exist within the crystals. However, in order for the reaction to occur, energy must be supplied to fuel this redox reaction. This is accomplished when everyday ordinary white light passes through the crystals. The reaction between the titanium and the iron absorbs the red, orange, and yellow light regions of the spectrum to feed that redox reaction, thus allowing only the blue light to pass through the crystals, resulting in that deep blue color seen in the sapphires every day. So you could say that a simple working definition for ORP is a solution's capacity for electron transfer known as oxidation or reduction that's given in millivolts. ORP is similar to pH in that pH indicates how acidic or basic a solution is based on the hydrogen ion activity within the solution, and the ORP indicates the reduction oxidation status of a solution based on the collective electron activity within that solution. Shown here is a section of a typical ORP scale. The full range is typically between positive 1,500 millivolts to negative 1,500 millivolts. And most of you are already familiar with what a pH scale looks like. When you look at the pH scale, an acid is defined as a substance that is capable of liberating hydrogen ions, and a base is a substance capable of absorbing hydrogen ions. But when you look at the pH scale at 0 millivolts, a solution is neutral. It's neither acidic or alkaline. But as you move above the 0 millivolts, the solution is considered to be acidic, and when you move below the 0 millivolts, the solution is considered to be alkaline or basic. An ORP system can be designed in a similar manner. Since a reducing agent is capable of accepting an electron and an oxidizing agent is capable of losing an electron, it can be said that the stronger the reducing agent, the more negative the ORP value, and the stronger the oxidizing agent, the more positive the ORP value. For example, an acid permanganate solution is strongly oxidizing, meaning it strongly attracts electrons from an ORP electrode, so the redox potential is highly positive. Opposite to that would be a sulfite solution, which are strongly reducing. They push electrons into the electrode, so the redox potential is strongly negative. Just like pH, ORP is based on the known Nernst equation to determine the equilibrium reduction potential of an installation that contains a conductive electrode and a surrounding conductive electrolyte within a process solution. When a chemically inert noble metal electrode is placed into a solution where an oxidation reduction reaction is taking place, the electrical potential appears at that measuring electrode on that noble metal part, and this potential is called the oxidation reduction potential. So now let's go over real quick what equipment you actually need in order to measure ORP. You need an analyzer, you need a sensor, and you need a cable. The analyzer's purpose converts the raw input from the sensor, calculates, displays, and transmits the ORP millivolt value of your process. The sensor itself includes two elements. You have a measuring electrode and you have a reference electrode. These can either be separate electrodes or they can be an all-in-one, where they're all in one body. However, unlike pH, since ORP is a direct measurement of the electrons in transit during those redox reactions, regardless of the process temperature, temperature compensation is not normally used in ORP measurements, and therefore there is no need for a temperature electrode. And as well as the cables that are going to be used really depend on the sensor that's going to be used. If you have an all-in-one, this could be an integral, or you could have individual sensors that have vario-pin connections, and you'll have separate electrodes. Go ahead. Okay, shown here you can see the basic ORP measurement circuit consisting of a reference and measuring electrode. Also, you see the voltage potentials that are present, which affect the accuracy of the measurement shown. The total voltages of this circuit is the algebraic sum of these potentials. E1 is the potential on the ORP metal surface in the process. E2 is the potential between the reference electrode and the electrolyte. And E3 is the potential that develops at the surface of the electrolyte and the process. The difference in these potentials between the two electrodes is what is actually being measured by your analyzer. These voltages give us an indication of the ability or actually the activity of those oxidizers or reducers that are present within your process solution. And the response time for the reading will vary with the concentration of the redox system. Higher concentrations are going to respond faster than lower concentrations. And you'll see here, because you use the same reference electrode, you'll have some of the same common problems that you see with your pH measurements. You can get coating of the the metal surface electrode that will cause your reading to be sluggish, as well as you could get some coating problems on your reference or plugging of the reference junction. And if your electrolyte gets depleted, you'll get errors in your readings as well. So now let's go into detail about the actual components of your electrodes. The first component of the ORP measurement system is your measuring electrode. Shown here, ORP is a photostensiometric measurement of the oxidizing and reducing power of the liquid. So the ORP measuring electrode is similar to that of the pH measuring electrode, except it's normally constructed of an inner noble metal. The most common metals used today are platinum, gold, and silver. Platinum is considered to be the standard because it has excellent chemical resistance, but it suffers slightly from something called chemiosorption. This is where when you place the platinum in a strongly oxidizing solution, the oxygen will bond to the surface of the noble metal, and in strongly reducing solutions, hydrogen will bond to the surface of the noble metal. And these surface coatings will insulate that platinum from the solution and will obviously decrease your response time to your process. Gold electrodes are used because they have properties that make them a good recommendation for those either strongly oxidizing solutions or strongly reducing solutions. However, it's important to note that gold is not recommended for use in applications that contain the cyanides, the bromides, the chlorides, because gold itself is not resistant to the corrosions that can occur because of these chemicals. This measuring electrode life and operational accuracy are adversely affected by the process chemical makeup. So it's very important that you choose the right metal for the right process. Since we cannot measure the voltage or charge buildup being generated by the constant acceptance or giving up of electrons on the ORP measuring electrode directly, we need to introduce the reference voltage and a way to complete the measuring circuit. Just as you see in pH, the ORP measuring electrode performs two functions. It provides a constant reference voltage and it completes that measuring circuit. Nurse discovered that when you have a silver-silver chloride pin immersed in a KCl electrolyte, as long as the chloride concentration remained constant, this combination would produce a constant millivolt potential. To connect these voltages to the process and then to the metal electrode to complete that measuring circuit, you need a liquid junction or diaphragm. There are various types of junctions out there. You have ceramic, you have porous, you have Teflon, sleeve, simple pour, double junction, triple junction. So there's different types of junctions out there that are used. And then the KCl within the reference electrode itself can be in two forms. It can either be in liquid or gel. In gel, the KCl solution will diffuse out of the junction at a slower rate. However, those cannot be refilled, whereas with a liquid KCl solution, and this is what we call a flowing junction because it naturally, or with overhead pressure, depending on how you have your installation, it flows out of the junction and into the process, and this can actually be refilled. And sometimes in certain applications, this liquid or flowing reference will solve some of the problems that you see in your measurements. So typically, since the same reference electrode that you use in pH measurement is also used in ORP measurement, you have the same problems. The reference electrode, because it's open to the process via the junction, is the weakest link in your ORP measurement loop. Shown here are just some of the typical problems that are seen with your reference electrode. Okay, so far we've discussed what is ORP and how is ORP measured. Now let's take a moment and go over some of the maintenance that is needed to maintain your ORP loop. So shown here are some of the basic do's and don'ts to assure the most accurate calibration is achieved. You always want to remember to start by cleaning your electrodes. You always want to use fresh buffer solutions, and you really want to pick a buffer solution that's closest to your actual control point for your process. And then just with pH calibrations, you have to allow ample time for your readings to stabilize during your ORP calibration. And we don't always recommend to do a calibration to a grab sample. Okay, a variety of cleaning solutions can be used depending on the coating effects of the process on the electrodes. Typically, a 10% solution of nitric acid, works well to remove any of the anti-corrosion chemicals or mineral deposits that collect on that noble metal. So first, to rinse, you want to rinse off your electrodes in just plain water and remove any heavy process coating buildup with just a soft brush. And then you want to immerse the electrodes in this cleaning solution for about 10 minutes. Be sure to agitate them regularly and, again, remove any remaining deposits with your soft brush. And then you want to rinse the electrodes in clean water and allow the electrodes to actually soak in this tap water for at least 30 minutes. This is just good practice to ensure that all that nitric acid, or if you're using hydrochloric acid, is removed from the platinum pin so that it doesn't affect your ORP reading. And then once you have your electrodes clean, you want to place them in a new clean ORP buffer solution and give it ample time to stabilize. If the display value is within about plus or minus 30 millivolts of the buffer values, the electrodes are considered to be cleaned and they do not actually need calibration, and you can put the system back online. However, if the value is outside of this normal standard tolerance, then calibration is required. However, typically, calibration is done once a month, but with, just like pH, more aggressive processes will require more frequent maintenance and calibration. ORP is a one-point calibration. However, it's common for two buffer solutions to be used, one to do the calibration and one that's just used as a check. It's always recommended to use fresh buffer solutions to avoid the possibility of introducing errors from contaminated or aged solutions. And you also need to note that just like your pH buffers, these liquid solutions have a limited shelf life and they should be used within that time frame. So you've already cleaned your electrodes, and now you want to make or you pour your buffer solution. You perform a single one-point calibration. You rinse your electrode. Then as a final check for correct calibration, you want to immerse the sensor in that second buffer solution to see if the reading is accurate. If not, the calibration should be repeated. It's good practice to note that if a span is found of 150 millivolts, change between the first solution and the second solution when you're using a quinhydrone buffer solution, we'll explain that more detail later in just a little bit, or a span of 30 millivolts if you're using pre-made solutions, then the platinum and gold measuring electrodes are considered clean and can be put online. Outside of that tolerance, they need to be re-cleaned and recalibrated. So to use today, there are three common types of ORP buffers. you can either purchase a pre-made stable ORP solution, or you can make your own ORP buffer solution. When making your own, there are two known types. The first is known as quinhydrome, and the second is known as light solution, but this one isn't used very often because you have to mix the sulfuric acid in it. So the most commonly used solution is the quinhydrone solution. This is where quinhydrone is mixed into those normally used pH buffers, your technical buffers or your NIST buffers, the 4, the 7. And it's mixed in there until it's saturated, meaning there's some crystals remaining undissolved. And this mixture results in some known millivolt solution. The top chart here shows those common millivolt values you can expect when using the standard technical buffer solutions with quinhydrone mixed in. And the bottom chart shows the standard expected millivolt readings that when you use the less seldom light solution mixture. So a quick example would be if I used a standard 4.0 buffer solution and dissolved quinhydrone into it at 25 degrees Celsius, and my reference electrode being used is a 3 molar KCl solution, then I can expect to see a millivolt reading of 253 on the display of my analyzer. When using a pre-made ORP solution, before you perform your calibration, you have to know two things. One, what is the reference solution of the electrode that I'm using? Is it 3 molar KCl? Is it 1 molar KCl? And what is the particular reference electrode system what is the particular reference system that this pre-made solution was based on? Was it, again, 1 molar? Was it KCl? This is to make sure that we ensure that we're comparing apples to apples. We have to convert the value to reflect the reference system that we're using, generally silver chloride. The label shown here on the slide is an example of Hamilton's pre-made ORP solution. As you can see, the label shows you 2 millivolt values. There's a 475 and there's a 680. The asterisk indicates that depending on which reference you are using, which millivolt value you can expect to see. This chart here shows you what you can expect when you have to either add or subtract the value of your pre-made solution to determine what you expect to see on the analyzer display if the values are not already given. To determine the correct millivolt of your pre-made solution, we have to account for the differences between the electrode reference value and the actual solution's reference value. Meaning, if your reference electrode that you have uses 3 molar KCl and the ORP buffer solution is a different reference system, the values will be different than what you expect. That you actually get will be different than what the value on the bottle says you will get. So let's go over an example quickly. This chart shows you if you have a pre-made solution of 350 millivolts and that you used a 1 molar KCl reference solution and the electrode being used is a 3 molar KCl solution, when a calibration is done at the 25 degrees C, you will not read that 350, but instead you will read an additional 22 millivolts, showing you a total of 372 millivolts on the display of the instrument. Yes, the millivolt difference from 1 molar KCl to a different molar KCl solution is minimal. However, if you have a pre-made solution that is based on the standard hydrogen electrode, or what's known as SHE, as shown on that Hamilton label just a second ago, the difference could be as significant as 200 millivolts. So here are some just troubleshooting tips for the most common problems that we see. If you're getting a slow response, this could be due to coating on the metal electrode or plugging of the reference junction. If you're seeing a noisy response, this could be because the reference electrode is either poisoned or the KCl could be depleted out of it. Noisy or drifting measurements could also be caused by old cable or a plugged reference junction. Okay, so let's go over some we have 2 troubleshooting scenarios that are most common. The first one shown here, had a customer call in and they said when they calibrate both their pH and ORP, they read perfect. Then when they put the sensors online, everything will work fine for about an hour or 2. Then the ORP value begins to drift down until it goes negative. However, the ORP value continues to read fine. they would clean, they would recalibrate the system, and then everything would work again. But after a couple hours again, the ORP would drift back down, and they would do the whole thing over again. For this scenario shown here, there could be two possible solutions or problems. The first is that the platinum is saturated or fouled. This one is difficult to correct. You can try to reactivate the platinum by inserting it in a strongly oxidizing or strongly reducing solution for about 8 to 24 hours. If that doesn't solve the problem, the second possible problem could be what's known as electrical polarization. For this, you need to actually check how the sensors are connected. If the platinum is connected to the solution ground terminal, this would be common if they're measuring using one sensor and they're measuring ORP and pH at the same time. Then you could try to move the measuring terminal, move the solution ground or the platinum pin into the measuring terminal, leaving the reference wired where it is. This would give you a high impedance for your ORP input, which will make it less susceptible to the polarization. However, if this solved the problem, this would mean that you could not, in that particular application and installation, measure pH and ORP with the same electrode. You would have to have two different installations. Okay, our second one, and this is the most common, so I just want to make sure that I drive home this point and explain it slowly and everybody understands it. I have an ORP solution that should read 350 according to my bottle. However, it's reading 372 on my instrument. Okay? Two different things could be happening. First, the customer believes that everything should match exactly, but in reality, ORP has basically a tolerance that is plus or minus 40 millivolts. So if you're within that range, it's acceptable. However, the second could be the concentration of the electrolyte being used in your measuring system, in your sensor, is different than that was used to make that pre-made ORP solution. This minute ago I discussed it, and I want to go over it in an example again. So let's take a look at that chart we saw just a moment ago. We'll go over it one more time. So if I have a pre-made solution that the label reads 300 millivolts, that used a 1 molar KCl solution, and the electrode that I'm using contains a 3 molar KCl solution, when I perform that calibration at 25 degrees C, I wouldn't read the 350 millivolts. Instead, I would read that additional 22 millivolts, showing the 372 millivolt on the display. Okay, so as a rule of thumb, the reference electrode, just like in pH, it is the weakest link in your measuring system, and it's about the case in 80% of applications. So selection of the appropriate reference, whether it be a gel-filled, whether it be a flowing reference, the different type of junction that's actually used, is critical to reduce these potential electrode problems, extend the life, and maintain measurement accuracy. Okay, so far we've discussed what is ORP, how is ORP measured, what equipment is needed to measure ORP, and how do you maintain your ORP system. Now let's take a moment and look at some applications. As with any measurement, the goals are always the same. You want to know, how can I get an accurate, reliable, and resourceful measurement with the least amount of maintenance? This is what everybody wants. But for many years, ORP measurements have caused their fair share of frustration because people didn't know the ins and outs, not like pH. But if the ORP is actually applied correctly, it will provide accurate the critical information that is needed. So ORP can be used to monitor and control in many industrial aqueous systems to correlate the millivolt readings to the sanitation strength of the chlorine present in the water. Various chemicals are commonly used to control the slime and producing microbes, but the most commonly used chemicals are chlorine. For chlorine to function properly as a biocide, it must be present in its oxidizing forms, either in the hypochlorous acid form or the hypochlorite ion form. Since addition of chlorine increases the oxidizing capability of the water, ORP provides a useful indicator of the effectiveness of the chlorine present in the water. However, since equilibrium between these three species is pH dependent, any changes in pH will be seen as a millivolt change and interpreted as an ORP change. when a standard ORP measuring electrode and reference electrode are used. So, to provide an accurate indication of the true chlorine present, we must compensate the ORP measurement for the effects of the varying pH. One way to do this is to replace that silver chloride reference electrode normally used with a pH measuring electrode as a reference electrode. This is that thing that we know as pH compensated ORP. So with traditional ORP measurement systems, you cannot differentiate between an oxidant change and a pH shift. By using a pH measuring electrode as the reference electrode, this allows you to recognize the difference between the two. Since the pH electrode is acting as the reference electrode, that stable millivolt value that it will generate will shift at the same rate as the millivolt change because of changes in pH. Advantages to using pH compensated ORP is that the process control is more reliable since the millivolt value given depends on the reagent concentration and not on the pH, as well as there is less maintenance because the measurement doesn't require a reference cell that could lead to potential junction troubles later on. Similar to Biocide Control, ORP can be used as disinfection of water as a critical step in minimizing the potential transmission of pathogens. Many facilities already established ORP as a primary approach to monitoring disinfection parameters because it offers many advantages of real-time monitoring for a rapid and single-value assessment of the disinfection potential of their system. Research shows that bacteria such as E. coli and Salmonella are killed within a few seconds if the ORP value is maintained between 650 and 700 millivolts. Research also indicates that when water is left at this range for about a few minutes, yeast and other more sensitive types of spore-forming fungi can also be killed. This table here was taken from an article published by some research done at the University of California back in 2004, which indicates E. coli and Salmonella species were killed within 30 seconds when maintained at that millivolt value. However, a disadvantage to this method is that a combination of ORP and ozone concentration monitoring is necessary to ensure proper water disinfection. This is because the resistant spore-forming decay pathogens and human parasites that are present in the water are highly tolerant to chemicals such as chlorine, bromine, and iodine, and other weak oxidizers that are commonly used for water disinfection. However, in clean, portable water, ozone has been proven to be a highly effective sanitizer at concentrations about 0.5 to 2 ppm. Here, the graph shows the relationship between the ozone concentrations and the ORP values are not linear. However, ORP can be used to give an indication of the buildup of the residual ozone and the antimicrobial oxidative status of the water. The chart at the bottom shows you some collected ORP and ozone values for various water applications. Okay, so this third application is Indigo Dying. This is where ORP is used in the process of dyeing fabrics the indigo color, because indigo in its natural form will not dye the fabrics because it's actually insoluble in water. So during the dyeing process, they have to add additives such as sodium hydrosulfite to use to convert the natural indigo to what's called white indigo, which is then able to stain the fabrics. They submerge the fabrics, or the submerged fabrics after the dyeing process are removed from the dye path and allow the white indigo to quickly react with the oxygen in the air, causing it to return back to its oxidized natural form, making this dyed solution on the fabrics, the stained fabrics, now insoluble in water. Again, insoluble in water again. So during the dyeing process, it's vital that the ORP be maintained low enough to ensure that the indigo remains in its reduced white indigo form so that they make sure everything's dyed, 100%. The last two applications that we'll talk about here are found in wastewater treatment, and we do have application notes on them as shown at the top. You can request it, and it's online. that goes into really more detail later. However, this first one is seen at electroplating facilities and different types of chemical plants where wastewater can contain toxic forms of hexavalent chromium, such as chromate and dichromate. EPA regulations require that this hexavalent chromium in the wastewater has to be reduced before the water can be discharged into the water system. This actually requires a two-step process. First, the hexavalent chromium is reduced to trivalent chromium, and then the trivalent chromium is can't even talk today, I'm sorry. I'm sorry, I'm tongue-tied now. Precipitated out as chromium hydroxide. As the oxidation reduction potential and the speed of the reduction reaction are closely tied to the pH value, ORP and pH meters are commonly used to ensure proper control of this reduction process at the different injection sites of the reducing agents. Okay, and this last application that we'll discuss today is cyanide wastewater treatment. Wastewater materials can contain alkaline rare earth metals and other heavy metals such as iron, nickel, and zinc. Cadmium, copper, silver, and gold are also commonly seen, as well as sometimes they can contain a deadly poison, cyanide. Obviously, cyanide-bearing wastewater found in mining and electroplating facilities and certain types of chemical plants are toxic and must be treated by oxidation with chlorine or chloride to bring the cyanide concentration within those EPA regulatory limits, again, before it can be released into the natural wastewater stream. Okay. You will also see ORP measurements in the production of magnesium, and in the electrofining, you'll see it in different various metals such as copper, silver, and nickel. So let's quickly go over what we covered today. It was a lot of information, and I got done a lot quicker than I thought I would. But we basically talked about what is ORP, how is ORP measured. We talked about the components of your measuring system, the different types of electrodes that are used. Then we talked about some cleaning and calibration, what to do, how to do it, and some solutions. And then we talked about some few examples of applications over there. So I just want to thank you for your attendance today. And I do believe we have some time for some questions that we received from the audience. And if we don't receive any questions, or even if we do, last time we had some good questions that were asked that we brought with us today that we want to go over again for you guys, just so we're on the same point. So let's start with those, Barbara, and we'll do those 5 while people are typing in any questions. If you don't have any questions, that is it today, and we'll see you again later.
Okay, great. Thanks, Sherilyn. We do have a few questions here. So first of all, if I'm measuring a pH and an ORP at the same time, if I perform a pH calibration, do I also need to perform a ORP calibration?
It is common for these types of systems to have 2 independent asymmetry potentials. So when you do a pH calibration, the asymmetry potential that is corrected does not automatically correct the asymmetry potential for your ORP system. So it's just good practice to follow behind and do an ORP calibration.
Oh, great. Second, I've heard that even with ORP, I should always be performing a 2-point calibration. Here you've stated that I should only be doing a 1-point calibration, which is more accurate.
Okay. Performing a 2-point calibration may make a user more confident of the measurement because it ties the measurement to 2 known millivolt values, offset and slope values. Also, you need to remember that the second point within your pH calibration is taking into consideration the aging of the pH measuring glass. So since ORP measuring electrode is a piece of metal, and given the 30 millivolts or so repeatability of the ORP sensor itself, it does not provide any more accuracy than a single-point calibration. So since ORP is also not temperature compensated, if the measurement is done at 25 degrees C, any benefit gained would be lost by doing a 2-point calibration. So it's just generally accepted to only perform a 1-point calibration.
Okay. Well, if I see a drift in my ORP value, where should I look first?
Okay, remember that the ORP responds to the oxidizing or reducing capability of a solution. So if the composition of the solution is changing, this means that your ORP value may change as well. However, if you are absolutely sure that your solution itself has not changed the chemical makeup of it, then you should always look, and you're using the right type of setup for your application, meaning the Biocide Control, you're using pH compensated instead of regular ORP Loop, then you need to look at your reference electrode, because remember that is the weakest link because it's open to your process, so any drifting problems could be caused by that.
Okay, just a couple more questions. What can I expect to see as a normal life of an ORP sensor?
Okay. Since an ORP measuring portion is constructed of platinum or gold, a metal, for the most part it should have a very long life as long as it's not broken and if the correct metal is used in that correct application. Remember, gold is not recommended for their cyanides and bromides because it's not chemically resistant to those particular chemicals. And remember, I mentioned before that even though platinum is the most commonly used, sometimes in other separate electrodes, sometimes you could have a combination electrode. So your measuring portion may not fail, but your reference portion will fail in those combination electrodes, so it's only going to last as long as that reference portion lasts.
Okay. Well, one more question. How sensitive is an ORP measurement?
Okay, at low levels, ORP can be difficult, but with an accurate electrode calibration, it encompasses a range of about that 30 to 40 millivolt range. The pH value of the system being measured is crucial. For example, try to maintain the free chlorine level under half a ppm can be challenging as the ORP value rapidly increases from 0 to 1 ppm. However, when you monitor those pH changes, keeping the level between the 0.75 and 1 or 10 ppm is achievable because it's just a nice gradual linear slope.
Okay, great. Thanks, Shirley, for answering those questions. And you had a wonderful presentation, and we'd like to also thank you all for attending and participating in this online web seminar. And also, we would also like to mention that this seminar was recorded and will be available for replay within 24 to 48 hours under the technical library of our web page. So we hope to see you online at our future webinars. Thank you, and have a good day.